Welcome back, fellow explorers of the cosmos. You've found your way here, which means part of you is still curious, still wondering what lies beyond the horizon of everything we know. I'm glad you're here. This channel is a quiet place for big ideas, a place where science meets wonder, where the universe whispers its secrets to those willing to listen. So get comfortable, let your mind slow down, and let's explore the cosmos together, one extraordinary fact at a time. The mission nobody expected. Just weeks after the Artemis II crew splashed down in the Pacific Ocean, NASA made an announcement that surprised almost everyone. Instead of going straight to the moon with Artemis III, the agency added an entirely new mission to the schedule, a crewed test flight in Earth orbit in 2027, designed to do something never attempted before in the history of human spaceflight. For the first time ever, a single crew aboard a single spacecraft would rendezvous and dock with not one, but two different commercial lunar landers in the same mission: Blue Origin and SpaceX. 2 rockets, 2 landers, 1 crew. It was described by NASA officials as one of the most complex missions the agency has ever undertaken. Not because it was going far, but because of everything it had to accomplish before humanity could safely return to the surface of the moon. Why not just land already? Many people asked the same question when the Artemis III announcement was made. Why not just go to the moon? Why add another test mission? The answer is simple, and it is the same answer that has guided every successful space program in history. Because the consequences of failure are too high to skip the hard steps. Landing humans on the moon requires a chain of operations so complex, so interdependent, that a single failure in any link could be catastrophic. The docking system between Orion and the lunar landers had never been tested with a crew aboard. The software interfaces between NASA and commercial systems had never been validated in space. The life support systems needed more evaluation time. Artemis III exists because the engineers who know this mission best decided that one more test, done right, was worth more than any shortcut. The Crew 4 astronauts were announced on June 9, 2026, as the crew of Artemis III. Commander Randy Bresnik, a retired U.S. Marine colonel and veteran of 2 previous spaceflights, who has logged over 7,000 hours in 95 types of aircraft. Pilot Luca Parmitano, an Italian astronaut from the European Space Agency, the first ESA astronaut ever assigned to an Artemis mission, and a man who once commanded the International Space Station. Mission specialist Frank Rubio, an Army physician and astronaut who holds the American record for the longest single spaceflight, 371 consecutive days in orbit. And mission specialist Andre Douglas, a Coast Guard veteran and systems engineer on his first spaceflight. 4 completely different backgrounds, 4 remarkable stories, 1 mission. Randy Bresnik, Commander Randy Bresnik, was born in California and graduated from the Citadel with a degree in mathematics. He became a Marine Corps aviator, then a test pilot, then an astronaut, selected by NASA in 2004. He has flown to the International Space Station twice, first aboard the Space Shuttle Atlantis in 2009, and again on a Russian Soyuz spacecraft in 2017, when he served as commander of Expedition 53. He has logged more than 7,000 hours across 95 different types of aircraft, and is a fellow of the Society of Experimental Test Pilots. Since 2018, he has worked within the astronaut office, overseeing the development and testing of Artemis spacecraft and systems. For years, he helped build the mission from the inside. Now, he will command it. Luca Parmitano, first European on Artemis. Luca Parmitano is Italian, a colonel in the Italian Air Force, a test pilot, and one of the most experienced astronauts in the European Space Agency. He has flown to the International Space Station twice, once in 2013 and again in 2019, when he became the first Italian to command the station. He holds a master's degree in experimental flight test engineering from one of the most prestigious aerospace institutes in Europe. He has logged over 2,000 flight hours across 40 types of aircraft, and on June 9th, 2026, he became the first ESA astronaut ever assigned to an Artemis mission. When the announcement was made, he was visibly emotional. He spoke about his family, about gratitude, and about the extraordinary privilege of being chosen to fly. Europe has powered Orion since the beginning. Now Europe sits at the controls. Frank Rubio, record holder. Frank Rubio is a man who knows what it means to wait. He launched to the International Space Station on September 21st, 2022, expecting to return home after 6 months. Instead, a leak in his Soyuz spacecraft forced an extended stay, and he ended up spending 371 consecutive days in orbit, breaking the American record for the longest single spaceflight. He is an Army aviator, a medical doctor, and an astronaut who has now spent more time in space than almost any American in history. He knows microgravity better than most. He knows what the human body endures over months in space. And that knowledge, hard-won, unexpectedly earned, makes him exactly the kind of person you want aboard a mission, testing the systems that will eventually carry humans to the moon's surface for weeks at a time. Andre Douglas, first flight. Andre Douglas is making his first space flight on Artemis III. He was selected as a NASA astronaut candidate in 2021, one of the most recent classes, and his background is unlike almost anyone else in the astronaut corps. He served in the U.S. Coast Guard, conducting search and rescue operations, maritime salvage, and drug interdiction missions. He then moved to the Johns Hopkins University Applied Physics Laboratory, where he worked on autonomous vehicles, space exploration systems, and undersea warfare platforms. He holds 5 degrees, including a doctorate in systems engineering. He was the backup crew member for Artemis II, sitting in mission control during every critical phase of the mission, learning everything he could. Now it is his turn. The first ESA astronaut on Artemis. The assignment of Luca Parmitano to Artemis III is historically significant in a way that deserves its own moment. The Artemis program has been described as an American return to the moon, but the spacecraft that makes it possible has always been partly European. The service module that powers Orion, provides propulsion, manages electricity and thermal control, and keeps the crew alive is built in Bremen, Germany by Airbus, using components from 10 European nations. Europe has been at the heart of Artemis since the beginning. Parmitano's assignment as pilot acknowledges that truth in the most direct way possible. A European sits at the controls of a spacecraft powered by European engineering on a mission that will determine when humans return to the moon. 3 rockets in 1 mission. Artemis III will require not 1, not 2, but 3 of the world's most powerful rockets to launch in close succession. First, Blue Origin's New Glenn rocket will carry the Blue Moon lander Pathfinder into orbit, where it will wait for the crew, potentially for several weeks. Then, NASA's Space Launch System will carry the Orion spacecraft and its 4-person crew into low Earth orbit. Finally, SpaceX's Starship, the largest and most powerful rocket ever built, will launch its own lander Pathfinder to meet Orion in orbit. 3 launches, 3 spacecraft, 1 crew. All of it coordinated with a precision that has never been attempted before in the history of human spaceflight. NASA described it as the most awe-inspiring coordination of heavy-lift rocket launches in history. Blue Origin's Blue Moon lander. One of the 2 commercial lunar landers that Artemis III will test is Blue Origin's Blue Moon Mark II. Blue Origin was founded by Amazon's Jeff Bezos, and the company has spent years developing the Blue Moon lander as its flagship contribution to human lunar exploration. The version flying on Artemis III is a Pathfinder, a test article, not the final flight version, but built to demonstrate the critical interfaces, docking systems, and operational procedures that will be needed when the real lander carries astronauts to the lunar surface on Artemis IV. The Blue Moon Pathfinder is designed to remain in orbit for multiple weeks, giving the Artemis III crew plenty of time to dock with it, enter it, test its systems, and gather the data NASA needs before committing to a moon landing. SpaceX Starship as a lunar lander. The other commercial lander testing during Artemis III is perhaps the most extraordinary vehicle in the history of spaceflight: SpaceX's Starship. Originally designed by Elon Musk as a fully reusable spacecraft capable of carrying humans to Mars, Starship was selected by NASA as one of its human landing system providers. The version that will fly on Artemis III is a Pathfinder, a crude lunar version of the spacecraft, modified specifically for docking with Orion and demonstrating the interfaces needed for a lunar landing. Starship is taller than the Saturn V. It has more thrust than any rocket in history, and it will meet the Orion spacecraft in low Earth orbit, dock with it, allow the crew to enter and perform checks, and then undock and return to Earth, all as preparation for the day it carries astronauts to the surface of the moon. Docking for the first time. One of the most critical objectives of Artemis III is something that sounds almost mundane but is anything but: docking. For the first time ever, the Orion spacecraft will demonstrate its docking system with another spacecraft while carrying a crew. This system, a precisely engineered interface that must physically connect two spacecraft traveling at thousands of kilometers per hour in orbit, had never been tested with humans aboard before Artemis III. The docking system must work perfectly. If it fails on a future mission, 4 astronauts could find themselves in lunar orbit, unable to transfer to the lander that was supposed to take them to the surface. Every test, every data point, every lesson learned on Artemis III feeds directly into the safety and success of that future moment. The spacer. One of the most unusual technical decisions in the Artemis III mission involves something called a spacer. On previous missions, the upper stage of the SLS rocket, the interim cryogenic propulsion stage, provided the final push to send Orion toward the moon. On Artemis III, which is only going to low Earth orbit, that upper stage is not needed for propulsion. But the rocket still needs to maintain the correct dimensions and structural interfaces. So engineers at NASA's Marshall Space Flight Center in Huntsville, Alabama, designed and built a spacer, essentially a structural stand-in that has exactly the same dimensions and connection points as the upper stage, but contains no engines, no fuel, no propulsion capability whatsoever. It is a placeholder built with extraordinary precision, machined from raw material and welded together over months of work, serving one purpose: to make the rocket the right shape. Longer time in Orion. The Artemis III crew will spend more time aboard the Orion spacecraft than any previous crew. Artemis II lasted nearly 10 days. Artemis III is expected to last approximately 2 weeks, possibly longer, depending on how the docking operations with Blue Origin and SpaceX proceed. That additional time in the spacecraft is not just a logistical fact. It is a deliberate scientific decision. The longer the crew spends in Orion, the more data NASA collects about how the life support systems perform over extended durations, how the air recycling holds up, how the water recovery systems function, how the crew's health and performance are affected by weeks in microgravity. Every additional hour in orbit is another data point that makes the eventual lunar surface mission safer for the people who will live there. A new heat shield. When the Orion spacecraft returns from Artemis III and re-enters Earth's atmosphere, it will do so using an upgraded heat shield, tested for the first time on this mission. The original heat shield design, while successful on Artemis I and II, had limitations in terms of the re-entry profiles it could safely support. The upgraded version is designed to enable more flexible and robust re-entry trajectories, giving mission controllers more options when bringing the spacecraft home. This matters enormously for future missions that will return from the Moon at higher speeds than Artemis III. The physics of lunar return are more demanding than Earth orbit return. Getting the heat shield right, testing it, evaluating its performance, refining the design, is exactly the kind of work that Artemis III makes possible. Entering the lander. Among the potential highlights of the Artemis III mission is something that has never happened before. Astronauts entering a commercial lunar lander while in orbit around Earth. NASA confirmed that crew members could potentially enter at least one of the lander test articles during docked operations. Imagine floating through a docking tunnel from the Orion capsule into the pressurized interior of a SpaceX Starship lunar lander or a Blue Origin Blue Moon, spacecraft designed to carry humans to the surface of the Moon. Checking the systems, evaluating the habitability, testing the interfaces. Every observation made inside those landers by trained astronauts provides invaluable information that cannot be obtained any other way. Not in simulations, not in laboratories, only in the real machine, in the real environment of space. 2 days with Blue Origin. The mission profile for Artemis III involves spending approximately 2 days docked to the Blue Origin Blue Moon Pathfinder. 2 full days of tests, checkouts, system evaluations, and technology demonstrations. The crew will evaluate the docking interface, test communications between the 2 spacecraft, assess structural behavior during and after docking, and gather performance data on every system that will eventually need to work flawlessly when the real Blue Moon lander carries astronauts to the lunar surface. 2 days may sound short, but in orbital operations, where every minute is planned and every action is carefully scripted, 2 days is an enormous amount of time. Enough to learn more about a spacecraft's true capabilities than months of ground testing ever could. 1 day with SpaceX. After completing docked operations with Blue Origin and undocking from the Blue Moon Pathfinder, the Artemis III crew will await the arrival of SpaceX's Starship Pathfinder and spend approximately 1 day docked to it. 1 day of tests with the largest rocket and spacecraft ever built, evaluating the same critical interfaces, checking the same systems, gathering the same irreplaceable data. The difference between 1 day and 2 days with the respective landers reflects the different designs and test priorities for each vehicle. Both encounters are essential. Both generate data that feeds directly into Artemis IV mission planning. And both represent something remarkable. A NASA crew floating between spacecraft built by 2 competing private companies, testing the future of lunar exploration in the most direct way possible. The multi-launch campaign. The logistics of launching 3 separate rockets in close enough succession to enable the Artemis III mission represent a scheduling and operational challenge of almost unprecedented complexity. Blue Origin's lander must launch first and reach a stable orbit where it can wait for the crew, potentially for several weeks. Then, SLS must launch within a window that allows Orion to rendezvous with the waiting lander. Then Starship must launch and rendezvous with Orion after the Blue Origin docking operations are complete. Each launch depends on the success of the previous one. Weather, technical issues, or delays in any element ripple through the entire sequence. NASA's mission controllers, working alongside teams from Blue Origin and SpaceX, will be managing the most complex multi-vehicle choreography in spaceflight history. Low Earth orbit advantage. One of the key decisions behind the Artemis III mission profile is the choice to conduct all docking operations in low Earth orbit rather than lunar orbit. This choice was deliberate and strategically important. In low Earth orbit, launch windows are more frequent, meaning that if any of the 3 launches experience delays, there are more opportunities to adjust the schedule without scrubbing the entire mission. The orbit also allows for more flexible timelines during docked operations. And critically, if anything goes wrong, the crew is much closer to home. Low Earth orbit is not the moon, but for the purposes of testing docking systems, evaluating lander interfaces, and validating the operational procedures that will be used on Artemis IV, it is exactly the right place to be. Bob Hines, the backup. Every crewed spaceflight has a backup crew. Astronauts who train alongside the prime crew, learning every system, every procedure, every contingency, ready to step in if a primary crew member is unable to fly. For Artemis III, NASA named Bob Hines as the backup crew member. Hines is a U.S. Air Force colonel, a veteran of the SpaceX Crew 4 mission to the International Space Station in 2022, and a former research pilot at NASA's Johnson Space Center. He has more than 27 years of service as an instructor pilot, fighter pilot, and test pilot. He will train alongside Bresnik, Parmitano, Rubio, and Douglas for every phase of the mission. His job is to be ready, completely, perfectly ready, and to hope, quietly, that he is never needed. The AX EMU spacesuit. Among the items NASA is evaluating for Artemis III is the AX EMU spacesuit, developed by Axiom Space as the next generation of lunar surface suit. While Artemis III is an Earth orbit mission and no spacewalks are currently planned, NASA is considering testing the interface between the AX EMU suit and the lander systems during docked operations. This kind of early evaluation is typical of how NASA approaches complex missions, finding every opportunity to test systems before they are needed in a critical environment. The AX EMU is designed specifically for the lunar South Pole, where temperatures vary dramatically and the terrain is rugged. Every test, every interface check, every evaluation of how the suit connects with lander systems makes the eventual lunar surface mission safer. CubeSats in Earth orbit. Following the success of CubeSat deployments on previous Artemis missions, NASA is again inviting both domestic and international partners to propose small satellite payloads for deployment from Artemis III. These tiny spacecraft, some no larger than a shoebox, can carry scientific instruments, technology demonstrations, or communications experiments into low Earth orbit. The Artemis III launch provides a unique and highly capable delivery mechanism for these satellites, reaching orbits that would be difficult or expensive to access any other way. For universities, research institutions, and small space companies around the world, a slot on an Artemis mission represents an extraordinary opportunity. A chance to fly science on the most capable rocket ever built. Communication challenges. One of the unusual technical aspects of Artemis III is that, unlike previous Artemis missions, the Deep Space Network will not be used for crew communications during the mission. The Deep Space Network, the global system of massive antenna complexes that tracked Orion all the way to the Moon and back during Artemis II, is optimized for deep space distances. For a mission in low Earth orbit, different communication systems are more appropriate. NASA has asked industry for input on potential solutions to ensure reliable, high-quality communications with the ground during Artemis III. This is exactly the kind of engineering problem that sounds mundane, but matters enormously. 4 astronauts in orbit need to communicate clearly with mission controllers at all times, through every phase of a highly complex docking sequence. Marshall Space Flight Center's role deep in Huntsville, Alabama. Engineers at NASA's Marshall Space Flight Center have been working for months on one of the most unusual components in the Artemis III mission, the spacer that replaces the upper stage on the SLS rocket. Material for the barrel section and the structural rings is being precision machined at Marshall, then prepared for welding operations that will join the components into a single structural unit. Marshall has been at the heart of American rocket engineering since the days of Wernher von Braun and the Saturn V. The engineers who work there today are the inheritors of that tradition, solving the same fundamental problems of structure, mass, and interface that their predecessors solved 60 years ago, with far more sophisticated tools and a far deeper understanding of the physics involved. Kennedy Space Center processing. At NASA's Kennedy Space Center in Florida, the hardware for Artemis III is already taking shape. The Orion Crew Module and Service Module are scheduled to be connected this summer, with engineers integrating the spacecraft's docking system, flying for the first time on this mission. Heat shield testing is underway, with individual blocks undergoing ultrasonic inspections before installation onto the heat shield structure. On the rocket side, technicians are integrating the engine section to the rest of the core stage, ahead of installing the 4 RS-25 engines. All solid rocket booster segments have arrived at Kennedy. Mobile launcher refurbishments are on track, and rocket stacking, the process of assembling the enormous SLS rocket in the Vehicle Assembly Building, is scheduled to begin during the summer of 2026. The machine is being built. The RS-25 engines. The 4 RS-25 engines that power the core stage of the SLS rocket have a history as long and distinguished as any component in American spaceflight. These engines, manufactured by L3 Harris, are direct descendants of the Space Shuttle main engines that powered 135 shuttle missions between 1981 and 2011. They burn liquid hydrogen and liquid oxygen at temperatures and pressures that push the boundaries of materials science. Each engine produces over 500,000 pounds of thrust. Together, the 4 engines provide over 2 million pounds of thrust at liftoff, working alongside the solid rocket boosters to generate the 8.8 million pounds of total thrust that lifts the entire vehicle off the pad. They are among the most complex and precisely engineered combustion devices ever made by human hands. 10 European nations. The European Service Module that will power the Orion spacecraft during Artemis III, as it did during Artemis II, represents a collaboration across 10 European nations: Germany, Italy, Switzerland, France, Belgium, Sweden, Denmark, Norway, Spain, and the Netherlands all contributed components and expertise to its construction. The module was assembled at Airbus facilities in Bremen, Germany, before being shipped to Kennedy Space Center for integration with the American-built Crew Module. When Luca Parmitano sits at the controls of Orion during Artemis III, he will be flying a spacecraft powered by his own continent's engineering, a fact that ESA Director General Joseph Aschbacher described as a powerful recognition of Europe's enduring role at the very heart of the Artemis program. What Artemis IV will actually do. Everything Artemis III is building toward, every docking test, every lander evaluation, every system check, exists to make Artemis IV possible. And Artemis IV is the mission that will actually land humans on the moon. Targeted for early 2028, it will carry a crew in Orion to lunar orbit, where they will transfer to a commercial lunar lander, either Blue Origin's Blue Moon or SpaceX's Starship, for the journey down to the surface. They will land near the lunar South Pole, a region no human has ever visited. They will step onto the surface. They will conduct science. They will spend days there before returning to Orion and coming home. Artemis IV is the reason Artemis III exists, and Artemis III is the reason Artemis IV will be safe. The lunar South Pole. The target for the first Artemis lunar landing is the South Polar region of the Moon, one of the most scientifically valuable and operationally challenging environments in the entire solar system. Permanently shadowed craters near the South Pole are believed to contain water ice, billions of tons of it, deposited over billions of years by comets and asteroids, and preserved in the eternal cold of shadows that have not seen sunlight since before the Earth existed. That water ice is not just scientifically fascinating, it is potentially the most valuable resource in the inner solar system, a source of drinking water, breathable oxygen, and hydrogen fuel that could sustain a permanent human presence on the moon and power spacecraft for journeys deeper into space. 1 mission per year. NASA's stated goal for the Artemis program, following the first lunar landing on Artemis IV, is to conduct approximately 1 lunar mission per year thereafter. Artemis V, targeted for late 2028, is expected to include the beginning of construction on a moon base, a permanent outpost at the lunar South Pole that will serve as a staging point for increasingly ambitious exploration of the moon's surface and resources. 1 mission per year, each one building on the last, each one expanding humanity's presence on another world. It is the most ambitious sustained lunar exploration program ever seriously planned, and it depends entirely on the success of the missions that come before it, including the complex, unglamorous, absolutely essential work of Artemis III, the Gateway Space Station. Beyond the lunar surface missions, the long-term architecture of the Artemis program includes Gateway, an international space station planned for lunar orbit. Gateway will serve as a docking point for future lunar landers, a way station for astronauts traveling to and from the surface, and eventually a staging point for missions deeper into the solar system. It will be built by an international coalition including NASA, ESA, JAXA, and other partners. Its first modules are planned to launch in 2027. Gateway represents a fundamental shift in how humanity approaches lunar exploration, not as a series of flags and footprints visits, but as the foundation of a permanent, sustainable presence on and around the moon. Frank Rubio's 371 Days. Frank Rubio's record-breaking 371 days in space deserves more attention than it typically receives. He did not plan to break the record. He launched on a 6-month mission and was supposed to come home in March 2023. But in December 2022, a micrometeorite struck his Soyuz spacecraft, causing a coolant leak that made the vehicle unsafe for crew return. A replacement Soyuz was sent, unmanned, and Rubio waited in orbit while the situation was resolved. He waited for months. He adapted. He continued working, continued conducting experiments, continued supporting the station. When he finally landed on September 27, 2023, he had spent 371 days in space, the longest single mission by any American astronaut in history. He landed, and he got back to work. Parmitano's near-death spacewalk. Luca Parmitano is calm, experienced, and deeply skilled. But his history in space includes a moment that could have ended very differently. During a spacewalk on July 16, 2013, water began leaking into his helmet. Not outside it, but inside, from a malfunctioning suit cooling system. The water accumulated rapidly, covering his ears, his eyes, his nose. He could not see. He could barely hear. He navigated back to the airlock by memory and feel, guided by the tether line, unable to communicate clearly with the ground. He made it inside with seconds to spare. The incident led to significant redesigns of the spacewalk suit water systems. Parmitano completed his mission, returned to space 6 years later, and commanded the International Space Station. He is exactly the kind of person you want at the controls of Orion. The Golden Age of Exploration. NASA Administrator Jared Isaacman used a phrase repeatedly in the Artemis III announcement that deserves examination: the Golden Age of Exploration. It is not empty rhetoric. The convergence of technologies happening right now in spaceflight is genuinely unprecedented. Reusable rockets that land themselves, commercial spacecraft capable of carrying crews, lunar landers built by private companies, spacesuits designed by startups, International crews flying on American spacecraft powered by European service modules. The barriers that once made space exploration the exclusive domain of superpower governments are falling. More nations, more companies, more people are involved in human spaceflight than at any point in history. Artemis III is not just a NASA mission. It is a product of this moment, this extraordinary convergence of ambition, technology, and global partnership. Andre Douglas and the DART mission. Before becoming an astronaut, Andre Douglas worked at the Johns Hopkins University Applied Physics Laboratory. And one of the projects he contributed to was DART, the Double Asteroid Redirection Test. DART was humanity's first attempt to deliberately change the orbit of a celestial body, a spacecraft launched in 2021 that intentionally impacted the asteroid Dimorphos in September 2022, successfully altering its orbital period. It was planetary defense, the science of protecting Earth from asteroid impacts, conducted for the first time in history. Douglas helped design and test systems for that mission. The same engineer who worked on protecting Earth from asteroids is now training to help send humans to the Moon. The breadth of what a single career in space exploration can encompass is remarkable. Bresnik's mathematics degree. Randy Bresnik, the commander of Artemis III, began his academic career studying mathematics at the Citadel, a military college in South Carolina with a rigorous academic program and an equally rigorous physical and disciplinary environment. The combination of mathematical precision and military discipline that defined his education at the Citadel runs through everything he has done since. As a Marine aviator, mathematical precision kept him alive in high-performance aircraft. As a test pilot, it allowed him to evaluate new aircraft systematically and rigorously. As an astronaut and commander, it informs every decision he makes about systems, procedures, and crew safety. Mathematics is not just an academic subject. For someone in Bresnik's position, it is a survival skill. The Orion docking system. The docking system that Orion will use for the first time on Artemis III is not just a mechanical coupling device. It is one of the most precisely engineered interfaces in human spaceflight. It must physically connect two spacecraft traveling at approximately 28,000 kilometers per hour in low Earth orbit, with tolerances measured in millimeters. It must create an airtight seal that allows crew members to float from one spacecraft to another without pressure suits. It must be strong enough to maintain structural integrity during docked operations when one spacecraft fires its engines. And it must release cleanly and safely when undocking is commanded. Every one of these requirements was tested extensively on the ground. Artemis III will test them in space, with crew aboard, for the first time. 3,800 suppliers again. Just as with Artemis II, the hardware for Artemis III is being built by a network of over 3,800 suppliers, spread across 49 U.S. states. Small companies and large aerospace corporations, universities and national laboratories, machine shops and electronics manufacturers, each contributing a piece of the puzzle. Each piece subject to rigorous quality control and verification testing. The economic footprint of the Artemis program extends far beyond the obvious names: NASA, SpaceX, Blue Origin, Boeing, Lockheed Martin. It reaches into communities across America, supporting jobs and skills that would otherwise not exist. When the SLS rocket rises from Kennedy Space Center on an Artemis mission, it carries with it not just 4 astronauts, but the work of tens of thousands of people who will never see their contribution fly, but know exactly where it is. The road to Mars. Every mission in the Artemis program is, in a fundamental sense, preparation for Mars. The life support systems being evaluated on Artemis III will eventually need to sustain a crew for a 2 to 3 year round trip to the Red Planet. The docking procedures being tested will be needed for Mars orbital operations. The radiation data being collected will inform shielding designs for the interplanetary journey. The commercial lander technologies being validated will evolve into Mars surface systems. Mars is not close. A crewed mission to Mars will not happen in the next few years, but every hard problem solved on the way to the moon, every system validated, every procedure refined, every lesson learned, is one less hard problem standing between humanity and its next great destination. Why commercial partners? The decision to use commercial lunar landers from SpaceX and Blue Origin, rather than a government-built system, represents one of the most significant strategic decisions in NASA's modern history. The reasoning is both economic and practical. Commercial companies can develop hardware faster and at lower cost than traditional government procurement processes allow. They bring innovation, competition, and private investment that amplify the impact of NASA's funding. Having two providers, SpaceX and Blue Origin, creates redundancy. If one system encounters problems, the program is not entirely dependent on it. And it establishes a commercial economy around lunar transportation that could eventually sustain itself without government funding, making lunar access sustainable in the long term. Parmitano's languages. Luca Parmitano is Italian. He studied in Naples and in Toulouse. He trained as a test pilot in Italy, flew with NASA in Houston, and commanded the International Space Station, a multinational laboratory where the working languages are English and Russian. He speaks Italian, English, French, and Russian fluently. This linguistic range is not incidental to his career. It is a product of the internationally collaborative nature of human spaceflight, where the most successful astronauts are those who can communicate across cultural and linguistic boundaries as naturally as they communicate across the technical ones. On Artemis III, working alongside 3 American crewmates in an American spacecraft about to dock with vehicles built by American companies, his multilingual background is one more asset in a career defined by them. What happens if something goes wrong? Space exploration carries risk. Every astronaut knows it. Every engineer designs against it. And every mission plan includes contingencies for when things do not go as expected. For Artemis III, the low Earth orbit profile provides significant safety advantages over a lunar mission. The crew is always within reach of a relatively rapid return to Earth. The backup crew member, Bob Hines, is training fully alongside the prime crew in case a medical issue or other problem prevents a primary crew member from flying. The multi-launch campaign has built-in flexibility to adjust timelines if any element experiences delays. And the entire mission architecture is designed conservatively, with margins, redundancies, and abort options at every critical phase. In spaceflight, optimism is a virtue, but preparation is a necessity. Science on Artemis III. While Artemis III is primarily a systems test mission, NASA is also exploring opportunities for science operations during the flight. The crew will spend approximately 2 weeks in orbit, time that can potentially be used for Earth observation, biological experiments in microgravity, technology demonstrations, and other scientific activities that benefit from the unique environment of space. NASA has indicated that specific science plans are still being developed, with input from the scientific community on what observations and experiments would be most valuable. The history of human spaceflight shows that crews in orbit consistently find ways to contribute to science beyond their primary mission objectives. And the Artemis III crew will be no different. The acoustic testing of Orion. Before any spacecraft flies in space, it must survive something almost as violent as launch itself: acoustic testing. The Artemis III Orion service module underwent acoustic testing at Kennedy Space Center's Operations and Checkout Facility in May 2026. Acoustic testing exposes the spacecraft to the intense sound pressure levels it will experience during launch, levels so extreme that they can shake components loose, crack welds, and damage sensitive electronics if the design is not robust enough. The testing facility generates sound waves powerful enough to be physically uncomfortable for anyone standing nearby. Every component must survive without damage or performance degradation. If it passes, it is certified for flight. The Orion service module passed. Standardizing SLS. One of the long-term decisions embedded in the Artemis III mission planning is the standardization of the SLS rocket configuration. Beginning with Artemis IV, NASA is implementing a standardized version of the rocket that eliminates the complex and delayed exploration upper stage in favor of simpler, more reliable systems. The agency is also no longer planning to use Mobile Launcher 2, whose development faced significant delays and cost overruns. These decisions reflect hard lessons learned over years of working with complex, bespoke systems, lessons that every engineering organization eventually confronts. Standardization reduces cost, increases reliability, and speeds up production. It makes the difference between a program that launches once every few years and one that can credibly achieve a mission per year. The backup lander decision. One of the most consequential decisions still to be made for Artemis IV is which commercial lander will carry astronauts to the lunar surface: SpaceX's Starship or Blue Origin's Blue Moon. NASA has not committed to a single provider. Instead, the agency has maintained competition between the two, with both companies developing their systems in parallel. The data gathered during Artemis III, from docking tests, system evaluations, and crew assessments of both landers, will inform that decision. It is possible that both systems will be used on different missions. It is possible that one will prove more ready than the other. The answer will not be known until the Artemis III data is analyzed. And that analysis begins the moment the crew splashes down. International partnerships beyond ESA. While ESA's contribution to Artemis is the most visible international partnership, a European service module, a European pilot on Artemis III, the Artemis program involves international partners from around the world. Japan's JAXA is contributing components to the Gateway Lunar Space Station. Canada contributed Jeremy Hansen to Artemis II and continues to develop advanced robotics for future missions. Other nations have signed the Artemis Accords, a framework of principles for responsible and peaceful exploration of space, as a signal of their intent to participate in this next era of human exploration. The Moon, when humans return to its surface on Artemis IV, will be reached through the combined effort of dozens of nations, united by a shared conviction that exploration is worth doing. What the crew will see. The Artemis III crew will not travel to the Moon. They will not see the lunar surface from closer than the Artemis II crew did. But what they will see is something equally extraordinary in its own way: the largest and most powerful spacecraft ever assembled by human beings, floating in orbit just meters away, connected to their own capsule by a docking tunnel they can float through. They will look out the windows of Orion at a SpaceX Starship, a vehicle taller than a 20-story building designed to land on the Moon and eventually Mars, hovering in the blackness of space. They will perform their checks, complete their tests, undock, and come home. And they will know with absolute certainty that what they just proved makes the next thing possible. The step before the step. History remembers the moonwalkers. It remembers the commanders and the firsts and the moments of triumph. But history is made possible by the people who did the work before the triumph, who tested the untested, who found the flaws before the flaws became disasters, who spent 2 weeks in orbit doing the unglamorous, essential, irreplaceable work of making the next mission safe. Artemis III will not land on the Moon. Its crew will not walk on another world. But without Artemis III, Artemis IV cannot safely happen. And without Artemis IV, the moon base cannot be built. And without the moon base, Mars remains unreachable. Every giant leap in history was preceded by steps that nobody remembers. Artemis III is one of those steps. And the people who take it are just as essential as the ones who will follow. And that brings us to the end of tonight's journey. 50 facts, one mission, and a step that will change everything that comes after it. Artemis III will not land on the moon, but without it, no one ever does. The crew of Randy Bresnik, Luca Parmitano, Frank Rubio, and Andre Douglas will spend 2 weeks in orbit doing the work that history rarely remembers, but always depends on. Testing, proving, making the next thing possible. The moon is still up there right now, waiting. And for the first time in over half a century, we are not just looking at it. We are building the road back. If you enjoyed this video, there is more waiting for you here on this channel. Every week we travel somewhere new, somewhere strange and beautiful and true. All you have to do is close your eyes and listen. Sleep well, fellow explorer. The next giant leap is almost ready, and so are we.